let's take a look now at G. In G, I have another type of root equation. This one's laid out a little bit different, as it has a square root given here and not an irrational exponent, but I can still solve it using some similar concepts. Now, one thing to notice here is I have two values of x. I have a root x minus 5, and then I have a positive x. So I want to eventually combine the two. In order to do that, I'm going to need to get rid of my root. So I can change this into the square root of x minus 5 equal to 7 minus x by subtracting x from both sides. Now I can eliminate my root by squaring both sides. So if I square both sides, I get x minus 5 is equal to, I'm going to change the order of this, but this would become x squared minus 14x plus 49, and you can get that through through distribution, or remembering that the product of a binomial squared is the square of the first term, the square of the second term, and double the product of the two terms. So now I have a quadratic equation over here on the right that I want to solve, so I'm going to make sure that this is set equal to 0 by subtracting x. That would give me a negative 15x, and adding 5, which would give me 54. Now I have a quadratic equation that I can solve, and I want to solve. In this case, it's quick to factor. X minus 6 times x minus 9. And negative 6 times negative 9 is positive 45, and through distribution I would get negative 15x. X times x is x squared. So my two zeros that I would get from this are x equals 6 and x equals 9. Now, I do need to make sure that I check this. In the process of solving, if you create a quadratic equation, and we did on this second step here that I wrote down, we created a quadratic equation. Oftentimes, you get an extraneous solution. So a solution through the algebraic method that doesn't actually solve the equation. So if I go ahead and I input 6 for x, I find that 6 is a solution. So x equals 6 is a solution to this equation. I could also input 9 here, and as I input 9, I found that 9 is not a solution to this equation. If I put 9 in on the left side, it is equal to 11, which is not a solution. So 9 is an extraneous solution, meaning the only answer for this is 6. You could also check this graphically if needed by graphing both sides of the equation and finding the intersection. Final problem here for this version of solving equations, or sorry, not the final problem, but the final one for this page. We have a rational equation. A rational equation is one with multiple fractions. So we often find that fractions are the most difficult thing to work with in solving equations. If we can eliminate the fractions, solving it becomes more simple. So we can eliminate the fractions here by actually taking a look at the denominators and factoring the denominators. So if I factor the denominators, it lets me know what values are present in each of the denominators, which allows me to get rid of the denominators. So for example, if I wanted to get rid of an x here, I would multiply by x, and that would eliminate x. It would also eliminate the x in this denominator, but I need to eliminate the x minus 2's as well. So in order to simplify this expression, I want to multiply by the factors of the denominator. So if I multiply this first term by the factors of the denominators, x and x minus 2, the x's would cancel, the x minus 2's would cancel, and I would be left with 10. Then plus, if I take the second term, 4 over x, and multiply it by x times x minus 2, the two x values would cancel, and so I would be left with 4 times x minus 2. Then equals, if I multiply finally the third term of the equation by x over x times 2, or sorry, x minus 2, the x minus 2's would eliminate, leaving me with 5 times x. So if I simplify this equation, now it becomes linear. And we should all be able to solve this. So if I combine my 10 and my negative 8, I get 2. If I subtract here, I get x. And so I have x equals 2. Now, I do need to be careful here and check for, again, extraneous solutions. If we know, or what we know about fractions, we know that you cannot have a 0 in the denominator. If I were to put a 2 into this denominator, this would give me a 0 in the denominator. So 2 can actually not be a solution. So if 2 is the only solution I get, and it's extraneous, then this equation actually has no solution. Now we can also check this graphically. So if I were to put 10 divided by x squared minus 2x into my graphing calculator, let me insert that x squared, and then add to that 4 over x, and then in the second equation do 5 divided by x minus 2, I could take a look at the graphs and look for intersections. And what I'm going to find, this is tough to see here, but what I were to find is that these both approach the same asymptote and actually will never intersect there. They approach the same asymptote here and will never intersect, and approach the same vertical asymptote there and will never intersect. So there is no solution to this equation. Let's take a look at another example. In I here we have an exponential equation. And so this exponential equation I'm going to begin solving by following a reverse order of operations. So I'm going to subtract 1 from both sides and attempt to again get the variable which is currently in an exponent by itself. Now before I deal with the exponential portion of this equation, notice that there's a negative out in front, so I'm going to divide by -1. Now there are multiple ways to do this. If 24 were a power of 4, it'd be a quick change of base here for 24, and then we could solve for the exponent. However, it's not, so what I'm going to do is I'm going to use the inverse of an exponential base equation with base 4, which is a logarithm of base 4. So if I take a logarithm of base 4 of both sides, on the right side, or sorry, excuse me, the left side, I would be left with just x plus 2. On the right side, I would now have log base 4 of 24. Now I can isolate x by subtracting 2 from both sides, and I have an expression that is the exact answer for my equation. Now commonly we have rounded this answer, so I can round this answer very quickly by using the change of base formula. So log of 24 divided by log of 2 minus 2. And this would give me approximate answer, and we'll round it to 2 decimals, approximately 2.58. So we can solve exponential equations through inverse operations using logarithmic equations. The remaining example is a logarithmic equation. In this logarithmic equation, we have 2 separate logarithms, both of the same base, and so we can combine them using our logarithmic properties. So our logarithmic properties would tell us that because the logarithms are being added, we can multiply together their inputs. Now we can eliminate the logarithmic equation by rewriting this using an exponential base 3. And so what we would get is 2x squared minus x is equal to 3 to the second power, taking each side of the equation as an exponent of base 3. This equation can be solved as 3 squared is 9. You can subtract 9 from both sides, and now we have a quadratic equation set equal to 0. Multiple ways to solve this quadratic equation. For this example, I'm going to go ahead and use the quadratic equation. So the quadratic equation, x would be equal to negative b, or b in this case is -1, so 1, plus or minus the square root of b squared, so -1 squared, minus 4 times a, which is 2, times c, -9. And this would be all over 2a, or 2 times 2. We can simplify this to get 1 plus or minus the square root of, inside the root I would have 1 minus 4 times 2 times -9, which would end up being a root 73 all over 4. So this is not a nice solution, but it's going to give us a solution. Now, remember for logarithms that the input value of the logarithm has to be greater than 0. So in my calculator, if I were to do 1 minus the square root of 73, and then divide that value by 4, it's going to be a number less than 0. So if I were to substitute that into this equation, it would not give me a correct solution. So even without checking this using the idea of the domain of a logarithm, I can limit my answer down to 1 plus the square root of 73 divided by 4. We could check this by substituting into the equation and seeing if it were to balance. We would find that this would be a solution. Now we can also give the approximated value here. I want to just head and circle just the full answer, but the approximated value can be typed into the calculator, which I've already done. This answer would be approximately 2.39. So you can check this through substitution or through graphing as needed. Let's take a look at another set of solving equations, problem number 44. In problem number 44, our equations are now systems of equations. So it says if the system has a solution, we're going to list it as an ordered pair or ordered triple. So let's take a look at 44a. In here we have two polynomial equations, both of them set equal to y. So y equals an expression in both cases. So the easiest way to solve this system of equations would be through substitution. So I could replace y, maybe the first y, and let's call this equation A, with equation B, x plus 3 quantity squared. And this would be equal to x cubed plus 3x squared minus 3x minus 9. Now I can simplify this or expand the binomial through multiplication. And I have a polynomial equation, which if I want to solve, I want ideally to be set equal to 0. So I would subtract x squared from both sides. So I'd still have x cubed. On the right side now, I would have 2, a positive 2x squared. Then I would subtract 6x from both sides, so that would give me a negative 9x on the right side. And subtract 9 from both sides, that would give me a negative 18. I can solve this polynomial through a grouping, factoring by grouping. So if I group the first two, they have a GCF of x squared, which would leave me x plus 2. If I take a look at the second two as a group, they have a GCF of negative 9, which would leave me with x plus 2. So now I have x squared minus 9 times x plus 2 equal to 0. And so I get the values x equals plus or minus 3 and a negative 3 if I were to solve the system of equations, or set these two equal to 0 and then solve them. Now, it wanted me to list my answers as an ordered pair, so I need to go back and find the corresponding y value. So I can take either one of these two equations and substitute back in the x value. So in this first instance, x is positive 3. Positive 3 plus 3 squared would give me 36. So one of my solutions would be 36. I can also substitute in a negative value for 3, and a negative 3 plus 3 quantity squared. This would give me 0. So negative 3, 0 would be a solution. And I can substitute in negative 2. So negative 2 plus 3 quantity squared would give me 1. So negative 2, 1 would be a solution. So this system has 3 solutions, each of them being an ordered pair. So this was a polynomial, a cubic function, and a quadratic. In part B, I see two equations. I see a parabola here. The top is going to be a parabola, and the bottom is going to be a square, or a circle. So we want to find the intersections of these two figures. If I take a look at the way that these are set up, I may notice that an easy way to actually simplify this would actually be through elimination if I wanted to do it algebraically. I'm not going to graph this, so I'm not going to worry about getting y to it by itself. I'm actually going to do elimination. I'm going to subtract b. I'm going to subtract a from b here. So I'm going to take b minus a. So this would be x squared minus x squared, which gives me 0. Y squared minus 2y, which can't really be combined, so I just leave that as y squared minus 2y. And then equal to 5 minus 2, which is 3. Now this is a quadratic equation that I can solve by getting it set equal to 0 and through a quick factoring method. So y minus 3 times y plus 1. Both of these factors can be set equal to 0, so y would equal 3 and y would equal negative 1. Again, I do want to go back in and find the corresponding x values, so I'm going to have to do a little bit of work here to find corresponding x values. Let me use equation A. I'm going to use equation A, and I'm going to rewrite equation A so that x is by itself. Or sorry, y is by itself, excuse me. So I get 2y equal to, oh, no, I do want to get x by itself. I want to solve for x here. So I'm going to have x squared equals 2 minus 2y if I subtract 2y from both sides, and then square root, so x equals plus or minus the square root of 2 minus 2y. Notice that again I created a square root here, so I have both positive and negative options, which means I'm going to have a variety of solutions here. So I can go ahead and substitute in my values for y. So if I start by substituting in positive 3, I'm going to get the square root of 2 minus 3, or sorry, 2 minus 2 times 3, which we should recognize is going to be an imaginary number, a non-real answer. Because we're solving a system of equations, we're not looking necessarily for imaginary numbers, but just ordered pairs and ordered triples on a graph. So this part is going to give me imaginary solutions, which for our purposes of solving here, we are not interested in. And so I'm going to move on to y equals negative 1. So if I go ahead and go back to this equation, and now instead of 3, I substitute in a negative 1, I'm going to get plus or minus 2. Remember, there should be a plus or minus in front of the square root. So this would be negative 1, positive 2, and negative 1, negative 2. So if you were to graph these two, you would notice only two intersections. Yes, y equals 3 is a solution, but it's going to give us imaginary answers, and because we were looking for ordered pairs, we're only concerned with the real numbers. Finally, problem 44, C, is a 3-variable system of equations with 3 different equations here. So we want to use the process of elimination here as well to eliminate variables down into a 2-variable system of equation. So if I label these, I'm going to go ahead and label them as A, B, and C. I'm going to use a couple methods of elimination here. So if I take a look at A and B, if I just add A to B, I don't even have to change any signs. I can just add A to B, and my y values will eliminate. So 3x minus 2x would be x, 2y minus 2y would be 0, and a negative z plus 3z would be 2z. And finally, negative 1 plus 5 would be 4. So this gives me a 2-variable equation. Now I can't solve this 2-variable equation because I have, again, 2 variables. But I can try to eliminate y. I've already eliminated y once. I can try to eliminate y a secondary way. And I can see I can do that here by adding b to c. B and c, if I add them together, the y values will cancel out. So negative 2x plus 3x, or 5x, sorry, would be 3x. Negative 2y plus 2y is 0. 3z minus z would give me 2z. And 5 plus 3 is 8. So let's call these equations D and E. Now I can combine D and E in a method that's going to simplify or eliminate at least one of the variables. So what I'm going to do here is I'm going to take D minus E. I'm going to take D minus E because I'll notice that the z's will cancel out. So 3x minus x would be 2x. 2z minus z would be nothing. And then 8 minus 4 would be 4. So I get 2x equals 4, and dividing by 2, I can solve for x. So x equals 2. Now I can solve for z by substituting back into either one of these two equations. So if I substitute this back into, let's say, equation D, I would get 3 times 2, which is 6, plus 2z equals 8. Then I can subtract 6. 2z equals 2, and z equals 1. So there's another portion of my solution. Now I can take both of these answers, z and x, and let's substitute back into one of the equations from the original problem to be able to solve for y. Let's just use equation A. Equation A would now become 3x, so 6, plus 2y, minus z, and z is 1, so minus 1, equal to negative 1. I can subtract 6 and add 1 to both sides to get 2x, or 2y equals a negative 6, then divide by 3, so y equals negative 3. So my final solution would be the ordered triple, with x being 1, y being negative 3, and z being, sorry, x being 2, y being negative 3, and z being 1. You could check this by substituting in each of the values for x, y, and z and see that it would satisfy each of the three equations. So here are examples 43 and 44 on solving equations, a variety of equations. As always, thank you guys for tuning in, and I'll see you soon. What's up, guys? Welcome back to another Algebra 2 review lesson here with Mr. Gaines as we prepare again for our final exam. In this video, we're going to go ahead and continue where we left off in the previous one. This is part 5 of our series, where we're going to take a look at solving various types of equations. So let's jump right into some example problems. In problem 43, it says for each of the following, use an algebraic method to solve or to find the value of the variable, eliminate extraneous solutions as needed. So anytime it says to use an algebraic method, we're going to have to show our work. Problem 43a is a linear equation. So in this linear equation, there's a variety of ways that we can go about solving it, but what I may want to do is to simplify the equation, and I can simplify the equation by distribution here. So if I distribute the 4, I'm going to end up with 4v minus 1 equal to 14. Now in most cases, you guys like to eliminate fractions. You don't have to, but we can eliminate the fraction here by multiplying the entire equation by 2. So if I multiply the entire equation by 2, I'm going to have v plus 8v minus, sorry, this should be 4v minus 4 if I distribute it correctly. 8v minus 8 equal to 28. So if I distribute that or multiply everything by 2, that eliminates a need for fractions. So in the same step, I'm going to combine the v and 8v as well as add 8 to both sides, and then I can divide by 9 and get that v is equal to 4. I can check this on the calculator pretty quickly by inputting 4 for v. And when I do so here, I get the left side of the equation is equal to 14, so v equals 4 is our solution. Taking a look at b, we have an absolute value equation. Now there are two variables of x in this equation, one inside an absolute value and one outside of an absolute value. I'm going to go ahead and try to get the absolute value by itself. So I'm going to subtract, x from both sides. So I would have the absolute value of x minus 4 is equal to the opposite of x plus 7. Now, to get rid of the absolute value, remember absolute value takes all numbers and makes them positive, regardless of what those numbers might be. So when I get rid of the absolute value, I have to consider two cases. I have to consider the case that we see here, just eliminating the absolute value. And I also have to take the opposite of the other side of the equation. So if I eliminate my absolute value, I need a second case where x minus 4 is equal to x minus 7. Now in such cases, I can go ahead and solve. So on the left, I'm going to add x to both sides and add 4 to both sides, and then dividing by 2, I would get 11 over 2. I could input this answer into the equation, and I would see that 11 over 2 is a correct solution. My second case, if I go ahead and subtract x's from both sides, I would get negative x is equal to, or sorry, negative 4 is equal to negative 7, which we know is not true, and so this case would give me no solution. Now we do have to make sure that we check, even though I only had one solution in this instance, a lot of absolute value equations will have two solutions. So we have to make sure we consider both cases when we remove the absolute value. In C, we see another example of that. The difference in C is we now have an inequality. So the expression is less than or equal to negative 22. So I'm going to go ahead and follow reverse order of operations first to get my absolute value by itself. So I would subtract 8 from both sides and then divide by a -2. Now remember, with inequalities, when I divide by a negative, I have to change the direction of that inequality. So this would say that the absolute value of x plus 11 is greater than or equal to 15. Now, in getting rid of my absolute value, I need to consider two cases where the absolute value, or where x plus 11 is greater than or equal to 15, but also where x plus 11 has a relationship to the opposite, or -15. Now remember, if I change the sign here of -15 and change it to negative, I need to change the direction of my inequality. So as I solve here, I'm going to get x is greater than or equal to, I'm going to subtract 11 to get x is greater than or equal to 4. And then I'm going to also subtract 11 on the other side to get x is less than or equal to -6. So this is an OR statement here. We could also write this as an inequality, so x would be from -infinity to -26 with a bracket, or from 4 with a bracket to infinity. These would mean the same things. So in this case, we have to consider, we see where considering both cases of removing the absolute value gives us two different portions of our solution. In D, we have a quadratic equation, 3x squared minus 6x. And let's assume that this just meant to be equal to 0. We're finding the zeros here. That's a little bit of a typo, but let's just set this equal to 0 and solve. Now, there's many different ways to solve a quadratic equation. The fastest and most efficient is if you can factor. And in this case, we can factor. We can factor by removing a GCF, 3x. So I can take factor a 3x out from both terms. And when I do so, I get x minus 2 remaining. Now, when you have factors of a polynomial that multiply together to give you 0, you can set each factor equal to 0 individually. So 3x would equal 0, and x minus 2 equals 0. Thus, we have two solutions, x equals 2, and adding 2 to both sides, sorry, x equals 0 by dividing 3, and then adding 2 to both sides, x equals 2. If I take a look at E, again, let's assume that this one was meant for equal to 0. I'm going to find that this one does not factor easily. It's not going to factor using real numbers. It could using imaginary numbers, but we're not going to worry about how to do that. We're going to focus on the real numbers. So there's a couple of different ways that I could solve this. Most of you guys know the quadratic formula, where x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Most of you guys will go that route if an equation is not easy to factor, and that's okay. You can definitely do that. What I'm going to show you here is how to complete the square, because completing the square is pretty quick and efficient in this method. So to complete the square, I'm going to move my constant to the other side. I'm going to subtract 13. You don't have to, but that is the easiest way to do this. Now, if I want to complete the square, remember I need a c value that is equal to b, which in this case is -4, divided by 2, and then squared. Sorry about these triangles popping up on the screen. Let's get rid of those. So -4 divided by 2 would be -2, and that squared would be 4. So I'm going to need 4 as my third term here on the left. So I'm going to add 4 to both sides. This gives me x squared minus 4x plus 4 equal to 9. This is nice because I can take x squared minus 4x plus 4 and change it into the quantity x minus 2 squared. Now, rooting both sides, I would get x minus 2 equals to plus or minus, sorry, this should be a -9, plus or minus the root of -9, and then I could add 2 to both sides. Now remember, the root of -9 can be simplified. The square root of 9 is 3, and because there is a negative inside the root, this would actually refer to an imaginary number. So our solution set here would be two solutions, 2 plus 3i and 2 minus 3i. If you solve this using the quadratic equation or the quadratic formula and you did that correctly, you would get the same answer. Let's go ahead and take a look at f. In f, I have a type of a root here, a cubed root equation actually. Now, in order to get x by itself, I'm going to again follow reverse order of operations, or SADMAP. So I'm first going to start by subtracting 4 from both sides. I'm going to try to get the variable by itself. And I would take the inverse of addition of 4 and subtract 4. Now I need to get rid of this 2/3 power. In order to do that, I'm going to take the inverse of 2/3 power, which would be the 3/2 power. So if I can take the 2/3 power to the 3/2 power, if you think about what we would do here is we would multiply those two things. That'd be 6/6, which would be 1. So what would happen is I would get x plus 3 to the 2/3 equal to 4, or sorry, x plus 3, no longer to the 2/3, just x plus 3 equal to 4 to the 3/2 power. I can simplify this by taking the root of 4. Notice that I'm creating a square root, so I need a plus or minus here. The root of 4 and then cubing that. So if I do this in my calculator, again, the calculator is not going to give me the plus or minus, but because I'm taking a square root, I do need a plus or minus. So this would actually be plus or minus 8. So x plus 3 would equal 8, and x plus 3 would equal -8. I can subtract 3 from both sides to get x equals 5 and x equals -11. And then you can check both of these answers. So both of these answers could be found or checked by inputting your answer into the variable for x and finding out that both solutions would work.